a series is just a sum of a sequence. So this Greek letter, which is called a sigma, means sum. So that is called a sigma. Try saying sigma to yourself once. Sigma. The sigma is just going to ask you to find the sum of a certain sequence. Remember, a sub n is what we used last time to talk about any sequence. So this notation for a series is just saying to sum or add up all of the pieces or elements in the series, starting with the first term and ending with the k term. So I don't have to take the sum of the entire series. I can take what's called a partial sum, because you're not counting the whole series, the whole sequence, you're just adding up parts of it. So looking at sigma notation again, a sub n is the explicit formula that we're going to use for a sequence, not recursive, explicit. That's the one where you can plug and chug. The n is called the index of summation. The index. It tells you what term to begin with. It's not always going to be 1. Sometimes you're going to do a partial sum of not the beginning part of a sequence, but the middle part of a sequence. And k is called the upper limit, which is nice since it's on top of the sigma, but that's where you're going to stop counting and stop adding the numbers up. So again, we're working with sequences, but we're just adding them together in sigma notation to find the sum of these sequences. So for example 1, we're going to use this sequence. Question, is that an infinite or a finite sequence?
That's a finite.
Why do we know the difference? Yeah, there's no dot, dot, dots at the end, which means it's a finite sequence. A and B are very easy. What is a sub 3? 13, because it's just asking what is the third term, which that's the third term in the sequence. And what is a sub 5? 17, because again, it's just asking for the fifth term in the sequence. Great. Now something else I can ask you about sequences is the series. I want to know, let me make sure I can show you both at the same time, the sum of this sequence starting with term 1, ending with term 3. So what we would do to find this out is we would say, okay, I'm going to add up literally the first 1, 2, and 3 terms. So the first term is 8, the second term is 10, the third term is 13. I literally just add them together. That's the sum from 1 to 3 of the sequence a sub n. And then like literally you just add those up. 8 plus 10 plus 13 is 31.
Wait, what? So where'd you get the 8 from?
I got the 8 from the series, or from the sequence. So this notation says to start with the first term, 8 is the first term, and then add every term in between it until you get to the third term, and then you can stop. That's the upper limit. So I'm literally just adding 8 plus 10 plus 13.
Is that what E means in between?
This is a sigma, so it's not E, it's a sigma. It's a Greek letter, capital Greek letter, and it does mean sum. It means add up the following.
So you get
Yes.
It's basically just a very confusing addition problem.
Correct. It is a very confusing addition problem.
keeps going.
Sequences and series are very elementary ideas with very complicated notation. Now, they can get more complicated when you start studying them in actual calculus. You would use them for other things, but at the basics, the elementary level of it, it is literally just an addition problem.
So you keep putting the numbers in between until you get to, if that number was 5, you go to 17.
Correct. You'd keep counting to 17, keep adding them up. So we can do that. Let's say we have the sigma of a sub n from 2 to 6. This time, what number am I starting to add with?
10.
The second term. So we're going to start adding with 10 plus 13 plus the next term in that sequence, which I can't see. So what is it? 14. 17. 20. If I add all of those things together, what do I get? A number, right. What number?
44.
Should be bigger than that? 74. Yeah, so we're adding up all of them from the second term to the sixth term. So from the index of 2 to the upper limit of 6. That's all that a series is. It is just a summation or an addition problem of a sequence. But it has cool mathematical looking notation.
Just quickly.
Yes.
last number?
That's actually a really great question. Did y'all hear what she asked?
No.
She said it's a finite sequence, and that this says 6 term, but we only added 5 things. So this upper limit is not how many terms we're adding together necessarily, because we didn't start at 1. We started at 2. So this is where we start, the index where we start. The top number is the index where we stop. Not necessarily that there are 6 terms, because we're only counting term 2, 3, 4, 5, and 6. It's only 5 numbers. So what I mean is, if we were looking at this sequence, this is term 1, 2, 3, 4, 5, and 6. That summation we just did in part D only wanted to add up these terms from the index of 2 to the index of 6. Not that there are 6 things necessarily, but just from 2 to 6, which is 5 things. If we went from 1 to 6, there would be 6 things. But we started at 2. That was a great question. Any other basic level question about understanding the notation of sigma? Okay. I don't know what that was. So we're going to write an expression for the sum of the series using sigma notation. So we're not just reading it and using it and adding stuff up. We're going to actually take a series that is written out and write it back into sigma or like simplified notation. So a couple things we need to be able to do this. The first thing we need to write sigma notation is we need to figure out what the formula is a sub n, which we did last time. So we need to look at it as if it was a sequence and figure out the pattern. And the second thing we need to do is find the upper limit, which is k. Because this is indicating, letter A is indicating that we are adding a partial sum from obviously the first term, because that starts it off, through, I don't know what's happening here, some other term. So we need to know what number 42 is in this sequence, because we don't know what number it is. We don't know what term number. So to find a sub n, we're going to go back to use the equations from last class. The equation from last class that we're going to use is this one. A sub n is going to be equal to a sub 1 plus n minus 1 times d, where d is the common difference. So we want to know the explicit equation for this series or sequence. I know that I would use this one and not the other one because these numbers are changing with addition or subtraction, not multiplication. So we use the arithmetic sequence. Okay? If we look at this pattern though, as if it was a pattern and not a summation, what's happening every time? We're adding 3 every time. So that means my common difference is going to be what number? 3. Okay. I also know my starting value. What is my starting value? -6. Okay, so I have all of the things I need to plug in. And I can write a more simplified looking explicit equation for this sequence. I would distribute the 3 and then combine like terms so that a sub n is equal to 3n minus 9. That's the explicit definition for this sequence. So we've done the first thing. We found a sub n. But now we need to know how many times we're adding this sequence to find my upper limit k. So what we would do is just simply solve for n. We know at some point this equation is equal to 42. We need to know what number that is. Well, that's just a regular little linear equation for me to solve. I would add 9 to both sides and then divide by 3. So n is equal to 17. The reason I need all of that is because I have to fill in every part of the summation. I needed to know the equation. I needed to know the beginning index, which obviously is 1, and then the upper limit, which is now 17. So I can put that all together and it would look like this. The sum of the equation 3n minus 9 starting at n equal to 1 and ending at the number 17. Whoa, what just happened? Let's talk about it. So what we did first, because we know when we are plugging in sigma notation, we need to fill in the beginning value, which is going to be 1, the upper limit, which we don't know, and the actual equation for the sequence. So I found the equation of the sequence. That's what we did last class, using the explicit notation. And then I used the fact that I know at some point the element is 42 to figure out what number in the sequence that is, 17. And so that's the upper limit. So if we're doing the second one, what do you notice about this pattern of numbers? Am I adding and subtracting or multiplying, dividing? Multiplying. And multiplying by what? Yeah, I'm multiplying by a half every time, because that denominator is getting bigger by 2 every time. So that means, since we're using multiplication, that this is a geometric sequence, and we're going to use a different formula from part A. Last class, we found out that the formula a sub n for geometric is going to be a sub 1 times r to the n minus 1. Okay, well, what's my first term? 1. Easy. What's my common ratio? 0.5, or a half, to the n minus 1 power. Well, there's my sequence, but I'm going to clean it up, and I'm actually just going to make this one be invisible, since it can. That's what I would use in sigma as my equation for the sequence, the definition for the sequence. The only other thing we need to find is the upper limit, but we're going to be using this last term to figure out the upper limit, because we know that's the number we stop adding on. So we're going to say 1 over 128 should be equal to 1/2 raised to the n minus 1 power. Now we need to solve for n. When we solved things like this before, this was in our exponential unit, we could never figure out what the exponent was unless what was happening with the bases. Say again?
They cancel each other?
Sort of like they cancel each other. How would they cancel each other? We could use a logarithm, but that gets into a lot of algebra that I kind of want to avoid doing. There's a simpler way to do this. Think about, let me maybe make it easier. Think about maybe when we had something that looks like this. Oops. How would we figure out what x was? No.
You gotta figure out
You would have the same base.
They would have the same base. 32 is the same as 2 to the 5th power. Once they have the same base, I would be able to say 5 equal to x. Do we remember doing this? After lunch, we'll remember what it means to take that number. So before we went to lunch, we were just remembering how to deal with this sort of equation to find the exponent. We need the bases to match. We could totally turn that to a 2 instead of a 1/2 by making it negative, but that's kind of complex. Is there a way we can make 1/28 the same base as 1/2? It would be 1/2 to what power? I think it's 1 bigger than that. Is it? I think it's the 7th power. 2 to the 7th. 2, 4, 8, 16, 30, 2, 4, 8, 16, 32, 64, 128. Yeah, 7. So it's the 7th power equal to 1/2 n minus 1, which means that 7 would be equal to n minus 1, or that 8 is equal to n. Now, all of that to be said, because we had a whole lunch in between starting this problem and finishing it. So what were we trying to do at all? What was the main goal of this problem?
figure out the top part of the sigma.
Very good. Yeah, the red part is to figure out the top limit, the upper limit for the sigma. So if we were going to write this whole thing, we'd say the sigma, or the sum of, starting at 1, of the equation 1/2 to the n minus 1, stopping at the number 8. That would be the sigma notation for that series. Starting at 1, ending at 8, the 8th term. That's the partial sum that we're taking. So we can find these sums using different formulas so that we don't have to sit here and just press plus, 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 plus on numbers, especially when the upper limit is something large. We want to be able to have a quicker way to find the sum, which is these formulas right here. Now there's a couple versions of it because there's a couple options for what you can have. If you have a general arithmetic finite sequence and you're trying to find the partial sum, if you know the last term, like they told you the last term, like the ones up at the top, you're going to use the top formula. S of n equal to n divided by 2 multiplied by the first thing and the last thing. But if you don't know the last term, you're going to do n divided by 2 times 2a sub 1 plus n minus 1 times d. So if you just have a dot, dot, dot at the end and you don't have the very last number, you're going to use the second term. Okay, so if we wanted to find the sum of these different sequences, obviously, yes, I can just add them up. But we're going to consider these to be really large sequences that we'd want to use the formula for. In the first example here, it says find the sum. Do we know the last term? Yeah, it gave me 20. And what term number is that? It's the 6. Whoa, I just wrote a 6 where that should be a 4. 4 or 5. It's the 6th term. So we know both the term number and the term. So we can use that first formula. That first formula would be S of n equal to n divided by 2 times a sub 1 plus a sub n. So we're finding the partial sum up to the 6th term. That means n is 6, a sub 1 is 5, and a sub n is 20. 6 divided by 2 is 3. 5 plus 20 is 25. So the partial sum of this series is going to be 3 times 25, which is 75. And we could double check this one, obviously, very quickly by just in our calculator or in our brain doing 5 plus 8 plus 11 plus 14 plus 17 plus 20, because that would be the sum of those series.
Why can't you just can you just add all of them?
Yeah. Yes, you really can just sit there and add all of them. And that's probably what I would choose to do in problem A instead of using this formula. But if I have something like problem B, do I know all the terms to be adding? No. So this is where it's going to be more helpful to use the formula instead of just brute force adding them. So we know the last term. That last term is 53, but do I know what term number it is? We have no idea what term number it is just quite yet. So we need to figure out what term number it is. So we have to do a little bit of work to make this happen. First of all, I need to know the pattern so that I can have a definition. Can anybody tell me the pattern here? Plus 6 every time. And since we're adding 6 every time, that means it's arithmetic, so it has a common difference. We're going to be filling in this formula. A sub n equal to a sub 1 plus n minus 1 times d. That's the formula for an explicit arithmetic sequence. That's from last class. Well, we know the first term is -7. Then we have n minus 1 times that common difference of 6. I'm going to go ahead and distribute the 6 and then clean it up so that a sub n is equal to 6n minus 13. That's the explicit sequence definition. We just then need to figure out what term number 53 is. So very similarly to how we found that upper limit a second ago, we need to figure it out again. Add 13 to both sides, divide by 6. That means it's the 11th term. Once I know that this is term number 11, I have everything I need to be able to use the formula. The formula is just written right above this. S of n equal to n divided by 2 times a sub 1 plus a sub n. Well, n this time is 11, because that's the last term. So we're doing 11 divided by 2 times negative 7 plus 53. Which, if we multiply that out in our calculator, we get 253. So that's the sum of that series. And yes, I could have just used the pattern and found the missing terms between the third one and the 11th one and added them. That's just about as much work as using the formula. In this third example, example C, do we know the last term? Did they tell us what the last term was? No, so we have to use the other formula where they didn't tell us the term. So the formula we're going to be using is this one. S of n equal to n divided by 2 multiplied by 2 times a1 plus n minus 1 times d. So things we need to know to fill in this formula. We need to know the term number. Do we know the term number? Do we know? Yeah, we know the term number. That's what we're going to plug in for all the n's. Do we know the first term? Yeah, we do. We can look at it. And do we know the common difference? Not yet, but can't I find it? What's the common difference here? Plus 3. All right, so I do know the common difference. That means I know every single thing to plug it into this formula, and I can just go ahead and plug it in. S sub 15 is going to be equal to 15 divided by 2 multiplied by 2 times negative 11 plus 15 minus 1 times 3. Throw all of that into a calculator or do it in your brain piece by piece. You get S sub 15 is equal to 150. So the sum of the series for 15 terms that we have here would be 150. That's the partial sum. Now, but all of these have been arithmetic. And pretty obviously, we're going to have a separate set of formulas for geometric because it's a different type of formula. We're not using addition, subtraction. We're using multiplication, division. The formula for finite geometric sequences or series is as follows. We're going to be finding S sub n if it's equal to a sub 1 times 1 minus r to the n divided by 1 minus r. R is the common ratio, n is the term number, and a sub 1 is the first term. All things that are decently easy to find. There's no difference in this one. We don't need to know the last term. We just need to know the final term number. We don't need the actual last term in these formulas, which is kind of nice. So we're going to find the sum here. To find the sum of this sequence, first of all, we need to know what the last term number is. They gave us the last number, but I don't know what term number it is. This one's 1, 2, and 3, but I have no idea what this one is yet, so we need to find it. Unfortunately, that takes a good amount of work. We're going to use the formula for a geometric sequence that we learned last class. A sub n equal to a sub 1 times r to the n minus 1 to be able to figure out what term number we're at. We know the first term is 2, and we need to know the common ratio. How is this changing every time? Times 3. So this is a 3. That's the sequence definition. But now we want to know 39,366. What is that for all of this? What does that make n? How would we first start solving for n? This is a review again of exponential functions. I will eventually match the bases, but the base is not isolated yet. Divide by 2. That's what I'm going to do very first. We divide by 2. 19,683. That's going to be equal to 3 to the n minus 1. And this, when there's just a base on the right-hand side, is where we want to match the bases. 19,683 is 3 to what power? I don't expect you to know this off the top of your head. The ninth power. Cool. 3 to the ninth is equal to 3 to the n minus 1, which means n is equal to 10. Once we know the first term, the n, and the common ratio, which we know all of those things now that we found n, we can use the formula for the sum. So we don't have to sit here and add and add and add and add and add over and over again, since we know this is the ninth term. That formula says that this would be S sub n equal to a sub 1, 1 over r, I'll move it in a second. I'm just rewriting the formula. We fill in everything we know. We know we're finding the sum of the first 10 numbers, where a sub 1 is 2. We're going to do 1 minus 3 to the 10th power over 1 minus 3. That's something we do in our calculators, probably not our head. And the sum of the first 10 numbers in this sequence is 59,048. That's what we'd get if we did that math. Okay, we'll go to example B. We're going to do the same thing. We want to know the sum of this series, but we're not going to do it just by adding numbers over and over again. We're going to use the formula. To use the formula, I need to know the first term. Check, I know the first term. I need to know the common ratio. Do you see the common ratio on here?
0.3.
Yes.
Well, make that negative. Yeah, negative 1/3 is actually my common ratio, because if you notice, that's the formula right there. And the common ratio is the thing in parentheses with an exponent. The last thing we need is the n. Do we know what term number that is? This is 1, this is 2, this is 3, this is 4. Do we know this term number? No, but we can figure it out really, really quickly. If we know that the actual formula should be 4 times negative 1/3 to the n minus 1, and our last term says 4 to the negative 1/3, or sorry, times negative 1/3 to the 10th, don't the bases already match? Doesn't that all look the same except for the exponents? Which means I can just set the exponents equal to each other, or very quickly figure out that n is equal to 11. Which again is just this number plus 1, because the exponent is always n minus 1. So if it's 10, that means the exponent is 11 minus 1, 10. Once I know all of those things, I can fill in the formula. S sub n, the formula again, just to rewrite it down, is a sub 1 times 1 minus r to the n, not squared, over 1 minus r. Fill in everything we know. S sub 11 is equal to a sub 1, that's 4. 1 minus negative 1/3 raised to the 11th power, all over 1 minus negative 1/3. It's a beast to type in your calculator, but it's totally something that you can just type in your calculator. There are no variables left on this entire side, so we can calculate it. It's kind of ugly, honestly, whenever we get to it. S sub 11 is going to be equal to 3.000017. approximately. Oh, let's switch over.
Doesn't matter how many decimal signs you get to the last square.
Yeah, this one, because you're multiplying by a fraction every time, is going to be kind of ugly numbers. If it was a fraction like a half that isn't a repeating decimal, it will come out to a regular number you don't have to round. But 1/3 is a repeating decimal, so you're going to have to round it eventually. Okay. Last little bit on this is, again, we're going to talk about the limits of these series. And again, the vocabulary comes back, convergent and divergent. So remember, convergent limits are an infinite series that has a sum or a limit. So if it actually goes to a number, it will be convergent. Divergent means it does not have a limit, or the limit is infinity. But these are much easier to do because we actually don't need Bobo, Bot, and Betsy. We could, but it's much easier. Infinite arithmetic sequences, so the ones with addition and subtraction, are always divergent because they either increase or decrease without bound if we're adding the numbers together. They're going to continue to get bigger when you add them up or continue to get smaller when you add them up. Infinite geometric sequences, if the R value or common ratio, if the absolute value of it is bigger than or equal to 1, so it's not some sort of true fraction, it's going to diverge. And it's going to converge if that common ratio's absolute value is some sort of true fraction between 0 and 1. And if it does converge, then it has an easier summation at infinity. The sum at infinity will be a sub 1 over 1 minus r. So a much easier equation to use. But this is only for when r is some sort of true fraction. So to determine whether each series is convergent or divergent, all we need to do is figure out what type of sequence it is and whether its common ratio is bigger than 1 or less than 1. So in this first one, we need to know what type of sequence it is. How are these numbers changing? Do y'all see? How could 2/3 become 1/3? Bless you. If we subtract 1/3, okay, but if we subtract 1/3, 1/3 minus 1/3, the next one would be 0. So we're not subtracting 1/3. What else could we do? Divide by, no, 2/3 divided by 2 means the 2's cancel out, becomes 1 over 3, so yeah. And if you take 1/3 and divide by 2, it's making the denominator bigger. 3 times 2 is 6. So we are multiplying by a half for each one of these. That's dividing by 2. Multiplying by a half is the same thing as dividing by 2. Fractions are division, divisions are fraction.
Do they have to put a fraction?
Yes. Don't put divide because that does not tell me a common ratio. Divide by 2 doesn't tell me the number we're multiplying by. We know that we're multiplying by the common ratio of 1/2. Does that mean that this is arithmetic or geometric if I'm multiplying? Geometric is the multiply. Arithmetic is the add, subtract, if you need to write that down. So we are using a geometric, and if we're using geometric, we need to decide if that r value's absolute value is greater than 1 or in between 1 and 0. Well, that's pretty obvious. Is 1/2 bigger than 1 or in between 0 and 1? In between 0 and 1. So this converges. It's a convergent series. And we can find the sum of this series if we just fill in this equation. S sub n equal to a sub 1 over n minus 1 minus r. What's the first term in this series? 2/3. And then we're going to divide by 1 minus the ratio. I assume you'd probably put that one into a calculator, which I know you can type in a calculator. That's 4/3. So the sum will converge on the number 4/3 as we continually add these out. Now notice that these are infinite. These are ending in your dot, dot, dots. So the formulas change when it's infinite because it's actually talking about their limits. What are they getting close to at infinity? That's a limit question. What about B? What is the pattern happening in the series B? How do I do all those changes? Yeah, +2, +2, +2. So is this arithmetic or geometric? If it's arithmetic, is it convergent or divergent? Divergent. Arithmetic is always going to be automatically divergent at infinity because we're continually adding numbers up. So it's going to continue to get bigger or subtracting numbers out. Yeah, this one's changing by multiplying by 3, right? So if it's multiplying, is that arithmetic or geometric? Geometric is the one where we're multiplying, which means it has a common ratio, and that common ratio is 3. Based on the notes that you can see at the top, if that common ratio is 3, which is bigger than 1, would this be convergent or divergent? Divergent. This is a divergent series. There's not going to be a limit at infinity because it's just going to keep getting bigger and bigger and bigger. It's technically going to infinity itself. So in these next examples, we're going to kind of put a few things together. We're going to find the first 5 partial sums, and then we're going to find the common ratio or difference to decide if it's convergent or divergent. So first 5 partial sums. Remember, the partial sums means we're adding the numbers up for the first 5 numbers. So my first partial sum, the sum of the first term is just literally, for this one, going to be 0.1. Great. The second partial sum means I'm taking the first 2 terms and adding them together. So the second partial sum is 0.11 because 0.1 plus 0.01. The third partial sum just starts adding the next number, which would add up to 0.111. The fourth partial sum, 0.1 plus 0.01 plus 0.001 plus 0.0001 would total to 1111. And the fifth partial sum, 0.1 plus 0.01 plus 0.001 plus 0.0001 plus 0.0000. Is that enough zeros? Yes, 1. Equal to 0.11111, because we're just adding these numbers up. But to answer the last question on this, after we do these partial sums, it asks me whether it's convergent or divergent. We need to know whether it's an arithmetic or a geometric sequence, first of all, and if it's geometric, what the common ratio is. So we try to figure out how this is changing. How are these numbers changing every time? It's close, sort of. Not times 10, because that makes numbers bigger. These numbers are getting smaller. What? Times 1/10, or divided by 10. So times a 10th. AKA moving the decimal 1 time each time. So that means, since we use multiplication, that this is a geometric sequence, and that r is going to be equal to 1/10. Based on the notes we took above, is that going to be convergent or divergent? convergent. And the limit, or the sum that is going to get close to at infinity, will be found by taking a sub 1 and dividing it by 1 minus the common ratio. Which is 1/9. Again, I know you can put stuff in a calculator. So these next few problems are going to be for you, B and C. I want you to find the first 5 partial sums and then determine if it's convergent or divergent. And if it's convergent, find the limit. So start by just doing the partial sums, the first 5 of them, and then you can look at the kind of sequence it is. Okay, so I've got my work for B up there, but I want to go over C because C is kind of interesting. Did anyone notice what type of sequence this is? Oscillating. It's the type of sequence like those oscillating fans that are just going to go back and forth between 1 and -1. We would have stopped doing the limit last class for the sequence just by noticing it's oscillating because it's not going to have a limit since it goes back and forth. But the series may still have a limit. We have to check. So we'll start with the partial sums. Here, the first partial sum will be 1 because it's 1. And the second partial sum will be 1 plus -1, that's 0. The third partial sum will be 1 minus 1 plus 1, that's 1. And the fourth partial sum will be 1 minus 1 plus 1 minus 1, that's 0. And the fifth partial sum will be 1 minus 1 plus 1 minus 1 plus 1. Whew.
It goes back and forth.
It does go back and forth. So it's still oscillating. The sum is oscillating each time we take it. What is the common ratio here? Times -1 every time, which means my R value, common ratio for it being geometric, is -1. Not necessarily. Remember, the rules we have now say we just need to find the absolute value of R. What's the absolute value of R? 1. Now, our rule said, again, that if it is greater than or equal to 1, what is it called? Divergent. So you still want to check that just to be sure that it is a divergent sequence. It'd be exactly equal to 1, which is divergent. If it was 1.1, it would be a convergent sequence. Sorry, 0.9, it would be a convergent sequence. Okay, so we're going to stick on this idea of just figuring out whether series converges or diverges, and if it converges, find the sums. But this time it's given to us in sigma notation. These are generally easier because in sigma notation, you can decide what type of sequence it is just by looking. With this pattern, something that looks like this. Was this the arithmetic sequence or the geometric sequence? Geometric is the one with the exponents, yeah. So this is a geometric sequence. And my common ratio in a geometric sequence is always found here in the parentheses. So this is geometric, where the common ratio is 0.75. If the common ratio is 0.75, does that mean it converges or diverges? Converges. And if it's convergent, then we can find the limit at infinity. We can find that sum at infinity. It's just going to be the formula. The formula is S. The sum is equal to a sub 1 over 1 minus r. We just need to know the first term in the sequence. Well, guess what?
Oh, it's 1. Oh, it's not 3.
It's 3.
Oh, that's right.
Your geometric sequences always have a sub 1 times r to the n minus 1, or k minus 1 power. So we know the first term. We know the first term is 3. And we're going to subtract that common ratio of 0.75. Again, I know you can throw that into a calculator, so I trust you to be able to do that on your own. If we were to add up this sequence all the way to infinity, the numbers would add up, getting closer and closer to 12. Notice again that the sigma notation has changed to infinity because we're finding these limits out at infinity, not necessarily a particular partial sum. Just at a really big addition problem. One that you wouldn't want to just sit there and add by yourself. You'd want to sit there and use the formulas. What about B? Is this arithmetic or geometric? Geometric again. What's the common ratio? Negative 4 over 5. And just while we're thinking about it, what's the initial value? 1, invisible 1. Yeah, bless you. So since we know that the common ratio is negative 4/5, does that make it convergent or divergent? Convergent. If it's a true fraction, something between 0 and 1, its absolute value, then it's convergent, and we can use the formula. S sub n equal to a sub 1 over 1 minus r. That first number is 1, and my common ratio is negative 4/5. 1 over 1 minus negative 4/5 would evaluate to 5/9. So the sum, when we add up this series all the way out to infinity, pressing add over and over again for all the numbers in the sequence, they'd sum up to 5/9. All right, we're looking at the sum from term 1 to infinity of pi over 2 to the n.
Divergent.
How do you know it's divergent?
Because I put pi over 2 in my calculator and it's 1.5.
Yeah, if you put pi over 2 in the calculator and you actually try to figure out what pi over 2 is, it approximates to 1.57 something. And if that number is bigger than 1, or at least the absolute value of it is bigger than 1, that's divergent. So that sequence, if we were to add it up in a series, would probably go off to infinity. It'd be continuing to get bigger and bigger and bigger, not getting to a particular number. And then last but not least, we don't have sigma notation for this one, so we actually have to do a little bit of work. The one thing I do know is what the first term is. What's the first term? 1. I just need to know the common ratio to decide if it has a limit or not. What's the common ratio here? Dividing by 2, right? Which we would write as times a half. Since I multiplied, I know that's geometric. R is equal to 1/2. Does that converge or diverge? It's convergent because the R value is between 0 and 1. So we can use the formula. The formula is a sub n equal to a sub 1 over 1 minus r. We know the first term is 1. And we know the common ratio is 1/2. If you calculate that, 1 minus 1/2 is negative 1/2. We'd get 2. So what we've done with series, let me walk us back through them. We learned how to read the sigma notation and find some partial sums, starting at the bottom number, ending at the top number. And then we have a whole bunch of formulas for finding the different sums given different pieces of information. We have some for finite and finite arithmetic, finite geometric. On this last page, we've been finding sums at infinity, which are like the limits of the sums. That's the one where the rules change for convergent or divergent. So there's a lot of itty-bitty things that are kind of difficult to keep all like focused in our brain when we're doing these problems. I highly recommend having these notes out all the time when you're using them, since we have to decide what type of function, what type of sequence, what type of series we're working with every time.